Are we good? Excellent, nice. So yeah, I think we're running a bit late, so I'm gonna try to go as fast as I can through these. Today I wanted to talk about reactive manipulation, and especially the role that tactile feedback plays from my perspective, or can play from my perspective, in enabling reactive manipulation. My interest, or my group's interest in tactile feedback sort of goes back to, goes back to the Amazon Robotics Challenge and sort of the aftermath from that, where we were tasked with building an autonomous system that was capable of picking up a variety of objects in a variety of scenarios, and deal with the challenges that come from occlusions and having just multiple objects dumped in a storage bin. And while many of the teams we develop working solutions, I think that it became clear that many of the things that you would naturally think that a system wouldn't have to do to be able to deal with dense clutter or object variability or constrained spaces, like, I don't know, gently palpating your way towards an object. If you want to grab, let's say, the champagne glass that is in the middle of the bin, or sort of accommodating the fingers on interesting geometric features on the boundary of the object, because maybe you want the fingertip to be on a corner, because that just happens to give you informative information. A lot of those techniques were not, it was impossible to implement them because we didn't have the right tools and we didn't have the right hardware, and we were all basically sort of driven by vision techniques with respect to perception and control. So I sort of became interested in sort of understanding how we could use tactile feedback and how that sort of changes our perspective on how we have to do everything else from perception to planning. This doesn't apply just to warehouse automation, right? So many things that you would think that are interesting from many of these scenarios where robotic manipulation sort of comes as a promise, comes to help us, operating in above, like, or using a tool in a home scenario, or interacting with humans, or ripping things apart if you're disassembling them. It is intuitive that tactile, or at least having a way to master that distal sensing, is important. So I want to talk about that. And to do that, I'll use three systems that we've been working on recently: cable manipulation, tabletop manipulation of rigid objects, and insertion. And while I will not describe in depth any of the systems, I want to give a perspective of them from the role that tactile is playing in making this work. So quickly, I think that we all realize that figuring out how to use tactile feedback, it is a difficult question, and in part because tactile feedback comes with many challenges, right? So in a scenario like this, where, let's say, tactile comes as an image or as some low-level feedback, as in the left, understanding how that sort of plays a role in all the manipulation chain that goes from controlling the interaction between the end effector and the object, or controlling the trajectory of the object, or controlling the trajectory of the arms that are controlling the end effectors. Understanding how that tactile information, which is very local in space and it's very local in time, how that affects upstream all that planning problem. It's quite complicated, and if you're not thoughtful during that planning pipeline, the most likely answer to that question is that actually it's not useful, right? unless you're careful on how you interact with an object or how you interact with the environment, it is likely that maybe the tactile sensors are placed in the wrong location, or your fingers are touching the object in a way that they don't render useful tactile information. So the question of how do we use tactile feedback, at least in my head, sort of gets transformed to how do we make tactile feedback useful, right? So how do we make sure that everything else we do on perception and on the planning pipeline makes it easier to consume tactile feedback? And along those lines, I want to discuss a couple points that I think that have been quite relevant or have sort of changed the way that we think about robotic systems. The first one is this idea of targeting contact interactions, which I was mentioning, right? So if you want to use tactile feedback, it comes natural to think that, well, you might want to make sure that you're contacting the objects in those places where the interaction will render useful tactile information. And by useful, that can mean different things depending on the system you're working on. It could be geometric features like in the image above, where you see a corner and that corner automatically gives you some information that can be blended with some vision estimation pipeline. But it could be something else if, for example, the goal is to sort of monitor the stability of a grasp. But the idea is that it has to render useful tactile information. And the second point is that if our system is going to be tasked with consuming that tactile information, because of the timely nature of that information, it has to react fast, which means that you probably want to have a good control over the dynamics of the interaction. In our case, we always like that the interactions we plan for, they define simple mechanical systems or systems with simple dynamics so that we can control them fast enough, which sort of leads to this notion of primitive behaviors that are well understood. Okay, so that's on one side, and then on the right hand side, so the second thread that I'll mention in the talk is sort of the role that actually tactile plays in the control loop of the behavior of the manipulation system. And this idea of partitioning that role into two key goals. The first one being controlling the contact state. So meaning if the mechanics that you're using to modeling the interaction assume that contacts are sticking, or assume that contacts are sliding, or assume that the grasp is stable, how do we develop a controller that uses tactile feedback that is targeted with ensure that that is happening, that the grasp is stable, that the contact is maintained, that the contact is sliding if it has to slide. And the second control loop is sort of maybe the more standard one, which is controlling the actual state of the object in the environment. So if I have to move an object from here, from there, how does tactile play a role in telling us where the object is in real time so that we can control its state. Okay, so I'll go again over these three systems, but from the perspective of thinking on how do we target these contact interactions, and then how do we partition the role of tactile. And I'll start with cable manipulation because it's the latest one, just in case I run out of time. Okay, so here's a system with two arms, two grippers that is tasked with picking up a deformable cable with relatively unknown dynamics. So the idea is that the cables could have different thicknesses made out of different materials. But the gripper has to pick up the cable and slide its fingers all the way to the end and then insert the end somewhere. And what I want to describe here right now is how we model the process of the gripper sliding its fingers along a cable in a controlled fashion. The basic idea is we have this division of the role of the control system. First, being able to control the state of the object, in this case, the state of the cable, which means for the most part, making sure that the cable stays sort of aligned at the center of the fingers so that it doesn't fall, and that it stays sort of orthogonal to the axis of the fingers. And then the role of the contact state controller in this case would be making sure that the cable can slide nicely when the fingers are trying to slide its fingers. So how do we monitor and control the gripping force between the fingers and the cable so that they can slide nicely? So we don't want the frictional force to be too large because otherwise they would get stuck. And we don't want the frictional force to be too small, otherwise the cable would just fall. And these under very large uncertainty on the material properties of the cables. So we start from this type of feedback that is coming from these sensors, which are probably well known by most people here. A specific instance of a gel site or gel slim sensors. It's an optical sensor with a camera inside that just gives us an image of the deformation of the skin of these fingers. So by tracking sort of the image that the camera is capturing, we can estimate the pose of the cable, and we can get an estimate of the distribution of forces when the cable is sliding or it's not sliding. Okay, so once we have that, the idea is that with a simple model of the interaction between the friction and the dynamics between the cable and the fingers, let's say we have a model where the cable is just a directional particle at the center of the finger, and we want to understand if we're pulling from that particle, this would be sort of the blue diagonal square on top of what it says there, the moving gripper. I don't know if you can see my cursor, but right there.
We can see, yeah.
Yeah, excellent, thank you. If we were to pull in a certain direction from the cable and that location, would that sort of rectangular block, would it move up or would it move down or would it turn? The goal is to make sure that rectangle sort of is aligned with the finger and it's at the center for as much as possible. So with a simple mechanics model like that, we can learn a linear model where the state is the pose of the cable in the fingers, and the input is the pulling direction. And we gather some data by just pulling from the cables. And then we learn a linear model, which then we can control with an LQR controller, which is feeding sort of the motion of the arm that you saw in the video that is pulling from the cable and is choosing in what direction to pull from. That's what it's necessary to implement the object state controller. We need a model like this, and we need feedback on where the object is, where the cable is in this case. And then on the right-hand side, the contact state controller, which is controlling the gripping force between the gripper and the cable, is tasked with making sure that the gripping force is large enough so that we get a useful tactile imprint to estimate where the object is, right? At the top row, if the gripping force is too small, we get a tactile image that it's not too distinctive. And if instead we apply too much force, like in the bottom row, the frictional interaction, the amount of friction between the finger and the cable is too large, measured right there by the deformation of the gel. So we have a simple PD controller that is modulating the amount of friction, and friction here in between brackets because it's really just amount of deformation it's an average estimate of the deformation of the gel, which is really controlled, like the shear forces. And when we put together these two controllers, the LQR controlling the robot motion and the PD controller on the gripping force, then is when we get behaviors like this, where the fingers are sliding on the cable and are trying to make sure that the estimation of where the cable is remains in the center, and if necessary, just regrasps if it detects that it's moving too far from the center, as you can see in the video from the tactile image. Right there, it went too far and it decided to just regrasp. Okay, so the basic idea is leaving aside the details of the mechanics of this primitive behavior, of this sliding behavior, the coupling the controller into these two controllers simplifies the development of the system. And this is a structure that we've been replicating, or we've sort of recreated over the past couple years in other systems. For example, in a tabletop object manipulation, which is a completely different mechanics, right? So the object is rigid now, and it's two palms instead of a gripper. It has the same kind of sensors now in the form of a palm instead of fingertips, but the same basic idea. And we want to get behavior like this, where there's sort of a sequence of primitive interactions, a pull in this case, now there's a grasp, and we want to be able to execute them on a levering motion in a reactive fashion, so that if we go there and we perturb it, then the system can react in real time. This is the kind of feedback that we get. So geometric feedback on the left and force feedback on the right. We can, if we target the right kind of interactions with the object, like in this case, we can see the edge of the object, we can get useful feedback that then feeds into the, let's say, the estimation of the pose of the object, or on the estimation of whether the object is slipping or not. And the basic idea is that once we get that feedback, with that can sort of populate these two tactile controllers. On the one hand, on the left hand side, the object state controller, where because we are targeting specific interactions that lead to simple mechanics, in this case it's just a pulling behavior, but we've sort of replicated these for different primitives, for grasping or levering or pushing. We can replan fast enough that if we maintain an updated estimate of where the object is, we can continuously update that plan that the palm and the arm they have to follow. And on the right hand side, the contact state control, where in this case, sort of the pulling behavior assumes that the interaction between the palm and the object have to stick. If the robot detects that the object is slipping, then it can decide to apply more force on the object in this simple pulling behavior. So we're interested in seeing how to generalize that. But here you see sort of the behavior of these two controllers independent from each other, where in the first one, the robot is trying to bring the estimate of the object to the goal. And on the second one, it's just applying more larger or smaller force when it detects that it's slipping. So it's trying to make the contact interaction, it's trying to enforce the expected contact interaction. Okay, so probably the most interesting aspect is this contact state controller. And in general, for the pulling behavior, it's intuitive. In general, what we have is a multi-contact interaction scenario. Let's say in this case, we have two palms manipulating an object that is also in contact with the ground. And there's this notion of grasp stability of the contact configuration. Let's say that if there's a contact on the right-hand side where one of the palms is sliding, there's a slip behavior. We can model the stability of this grasp by sort of making an estimate of the friction cones of each one of the contacts, and then make an estimate of where the actual contact forces are and how far they are from the edges of these friction cones. And then pose an optimization problem that makes an optimal or an informed decision as to what should be the reaction of the palms in terms of reorienting themselves or applying more or less force to sort of improve the stability of that contact configuration. So this means an optimization problem where we're trying to maximize this, what we call the margin of stability, or the margin to the edge of the friction cones, subject to the standard constraints of stable manipulation. So there has to be force equilibrium between the contact forces on the left and the external gravitational wrench on the right, and subject to the contact force constraints. So forces have to be positive, and they have to be inside the friction cones. So we're searching for the reconfiguration of the palms that sort of would maximize this margin of stability. In practice, because we want to be able to consume tactile feedback and we want to be able to react, let's say, to sleep events fast enough, we have to solve this optimization problem very fast, let's say at 100 Hertz or 50 Hertz, depending on the how fast the system is moving. And the margin is a non-convex cost, and this is also complicated by the fact that the force equilibrium constraint is bilinear, so it depends both on the position of the contacts as well as on the contact forces, and those two things are linearly related to each other in that constraint. So we have to convexify the cost function and linearize around the previous equilibrium to be able to solve this fast enough. So using the standard techniques that are used commonly by the locomotion community. But once we have that, then we combine those two controllers, then we can start to generate these regulating behaviors where, let's say that the robot wants to keep an object in a particular location. This is all constrained with one primitive behavior. It's sort of replanning where the trajectory of the object to go to that nominal position, as well as replanning the contact force that it has to exert on the object in real time. You can develop these for different primitive behaviors, and then if we know how to plan through, how to choose which behavior to execute at every time, then we can do these more dexterous manipulation of objects, still within a reactive framework. The problem of sequencing these primitives and choosing sort of the optimal strategy to combine them, that's still an open problem. And in this case, we use a graph-based search to sequence them, but we exploit the fact that we know the geometry of the object. And in general, when we want to execute these for objects with multiple objects or objects with unknown geometry, that's still an open problem. But the point is that, again, the combination of those two controllers generates or enables this reactive behavior. And the last system that I wanted to show, I don't know how much time do I have.
Few minutes.
Few minutes. Okay, so I'll just go quickly. This is sort of using the same strategy, but for a packing or insertion behavior, which has a very different dynamics, right? In part because one of the key issues here is that the interaction with the environment, it's more complicated, and if we want to control sort of the alignment between the object and the whole, the interaction behavior between those two elements is it's not observable to large degree. So it's more difficult to use a model-based approach to guide interaction. So we have to rely on learning policies that that are searching for the right kind of tactile interactions that are informative. But the interaction between the gripper and the object, it's still something that we can control, right? So we want to make sure, we want to search for the right alignment between the object and the hole, while making sure that the gripper and the object stay in some stable equilibrium, in some stable grasp. So it's the combination, again, of these two behaviors, where there's some learned policy that is trying to do an insertion, while there's some model-based controller that is making sure that the object is not slipping on the fingers, that is getting the job done here. And for controlling the stability of the grasp, we use this notion of incipient slip detection, where by tracking the interaction between the object and the gripper, we can allow the object to receive forces as long as there's no danger of slipping. And when it detects that it's about to slip, sort of the controller doesn't let that happen. So this low-level controller is sitting underneath the exploration policy for learning the packing behavior, which I'll just skip here for the sake of time. But it's basically sort of, this is still ongoing work where we use reinforcement learning to learn to map directly tactile streams of information to an alignment policy. All right, so in summary, how do we use tactile feedback? The key idea is that we should be thinking of how do we make it easier to use tactile feedback? How do we sort of reformulate, especially on the planning pipeline, our thinking so that it is more convenient to use tactile feedback? Key to that is targeting contact interactions that make it easier, and partitioning the role of tactile control into controlling the object state and controlling the contact state. And I just want to thank all the students that did all the work: Francois, Siyuan, Yu, Xiaoxing, Niha, and Jose, who have been working very hard to make this happen. Thank you, everyone else, for listening.
Professor Rodriguez for sharing. Okay, so there's a question from Shan. So in the cable manipulation project, how did you get the ground truth of the cable trajectory?
The ground truth of the cable trajectory in the fingers. So the key idea here is that we don't have to know where the cable. I mean, the dynamics of the cable is very complicated, and it can be modeled if you know enough about the particular cable. But in this case, we don't rely on any estimation of where the cable is, except for the first peak, or how the cable moves outside from the small region that sits in between the fingers. So we know where the cable is when it's in between the fingers. We just use image processing, standard image processing algorithms to sort of make the best fit of the contact patch between the fingers and the cable, and then we just fit an ellipse to that to get the axis of the cable. But outside, wherever the cable is outside the fingers, we don't care to first order. I mean, if you had to do a more complex manipulation with a cable, let's say tying a knot or untangling it, then you do care about with the state of the cable in the general sense. But to generate this sliding behavior, the only thing that we care is where it is in between the fingers. And to estimate it, we just use computer vision techniques to estimate it directly from the image.
I have a question about the tabletop manipulation project. So have you think about you can also use vision for locating the objects and using a force torque sensor at the wrist to measuring the disturbance from the external world? So is there any reasons or advantages of using a tactile sensor instead of vision plus force torque sensors?
Yeah, that is a great question. I think that there is no doubt in my mind, or probably in anyone else's mind, that vision is necessary to solve this problem. And sort of this study was focused on understanding how we can use tactile feedback, but you can't really solve this problem in the general fashion without knowing roughly where the object is initially. So if it's not, at the very least, to get an initial prior estimate of where the object is, at the very least for that, you need vision. But I think that vision can play a much more important role. And actually our current work, which we're doing right now, is understanding how these fits, or how this sort of synchronizes with the standard techniques now on using affordances to predict where to execute certain behaviors, right? So in this case, this works because we know it's a box, and we can locate the box, and we know how to contact the box. But if you want to do this to objects with general geometry, the right thing to do there is to use vision to guide that decision of where you should contact the object, where you should execute a push or a pull or a grasp. And that decision depends on the overall geometry of the object that can be captured with vision, but it also depends on the local features of the object so that you contact them on places that generate useful tactile feedback. And vision, again, can plays an important role there. So let's say, how do we go from a point cloud representation of the object into understanding where we should sort of contact the object to execute a push or a pull? I think that is a very interesting problem.